Hello and welcome to Robotics 101, an introduction to robotics for manufacturing. I'm Kyle Squillis with Purdue Manufacturing Extension, and alongside me today are our other MEP centers from Illinois and Iowa, CIRAS and IMEC. Our MEP national network exists all across the country. You can see our Iowa, Illinois, and Indiana states are highlighted in yellow, in addition to the other centers in every state. Our iSmart program, and that stands for Implementing Small Manufacturer Assistance with Robotic Technologies. It is a federally funded program designed to support automation adoption and implementation for U.S. manufacturers in those three states. This is going to take place in the next 18 months. Our focus is on quick wins in manufacturing adoptions, meaning faster paybacks than are normally accustomed to in traditional robotics. We're going to identify opportunities, help you develop the business case for these applications, and connect these manufacturers to the resources that you need, such as distributors, integrators, and training resources. And we will assist by preparing you with the deployments, as well as the post-deployment follow-up. Our agenda today looks like this. Why robotics for manufacturing, and how can you make it work for your center? Cobot versus robot. How does a collaborative robot compare to a traditional industrial robot? And which one is right for your plant? We're going to look at several applications along with some videos. And then we'll break down the iSmart resources and support a little bit further for you. So why consider robotics? If you have high turnover in any dangerous, dirty, dull cells in your plant, the operators just don't want to do these jobs. They're unmotivated. It can be dangerous. It can be an ergonomic issue. These might be opportunities for robots or cobots to be deployed. Production bottlenecks. Let's say you have a CO2 laser and you upgrade to a fiber laser. That can be quite an efficiency gains on the cutting side, but then your bottleneck might be then on the processing side, where you need to add a person or potentially some automation to make up for that increased speed. If you have a lot of rework and quality issues, again, robots are good at repetitive, consistent, accurate tasks. They might be the solution for solving some of these human errors that take place in the plant. Part traceability, date verification, high precision dexterity tasks. We talked about ergonomics. Repetitive motion is a big one. And then finding skilled workers. Manufacturers have been having trouble finding those skilled workers to fill these jobs that are quite demanding in a manufacturing environment. If you're adding a shift going to lights out manufacturing, cobots could potentially be a solution. Let's look at the types of robots that are out there. Start with the most common and articulated, followed by delta or parallel, sometimes called spider robots, SCARA robots, and Cartesian robots. Articulated robots are suitable for many types of applications. They have the widest range and are masters of some, such as machine tending, welding, and material removal. They're flexible, their dexterity is terrific, the mounting is very easy. However, the cost can be expensive, especially when you talk about the industrial side of an articulated robot. Their precision is good. However, some of the cobots, when sped up to the max, don't have quite the same repeatability and precision that the industrial line has. Speed as well on the cobot side. Cobots can be quite a bit slower than traditional industrial robots when put into collaborative mode. And we'll talk about some of these different modes here in a bit. Selectively compliant articulated robot arms, or SCARA robots, are really suitable for a lot of assembly and dispensing applications and pick and place. Their reach and payload is limited. They're much smaller than articulating robots. Dexterity is limited, as well as their range of motion. So these can be good for circular or oval shaped work tables because of the They operate on a 2-axis system with the head pivots on a bit of an arc compared to the Cartesian coordinated XYZ robot system. They do have good speed and precision, and their cost is much less than some of the other robots, and their footprint is quite small as well. So in a compact area, these might be a good solution for you. Delta parallel robots. These are high-speed robots that are really good with pick-and-place assembly and inspection. Somewhat limited to their lower payload and how you can mount them. They are really intended to be mounted from the ceiling, and that can be beneficial for a lot of applications, but that can also be a hindrance. So their dexterity in mounting certainly is a limitation. And their cost, again, is on par with the SCARA robots, similar size. They do have some larger ones, but the average parallel robot is a desktop type of model that can be fit into a compact space. Cartesian robots are very much suitable for custom applications, picking and placing, dispensing, assembly, and inspection, similar to a lot of the applications that we just looked at with the Delta robot. Again, these are relatively compact, relatively low cost, move in the XYZ direction, and are built on these 80-20 type of rail systems, which can range from small to very large and have multiple heads on them even. Their dexterity is somewhat limited just because it's the rotational axis is not in play here like it is with an articulating robot. These are very suitable though for custom applications, particularly pick and place and inspection. You can set up multiple operations within one of these robot cells when you have stations programmed and different tasks for the robot arm to do at each station. Comparing these, you're going to see each of these have pluses and minuses. With the articulated version, certainly with industrial robots, high speed and high precision would be checked off. In this case, they're assuming the articulated robot is a collaborative robot. Speaking of collaborative robots, so what are these things? They're designed to work alongside humans and not necessarily have to be caged, although safety and caging can be done. But they do have human type features. And what I mean is the payloads are similar, the speeds are similar to humans, and it's often a good first step into robotics. The price point is much lower than a traditional industrial robot, and you don't have to justify the purchase through having to produce millions of parts on a project. This can be a job shop type environment or medium production volume, suitable for the cobot speed and payload. Because of the relatively low cost, there is a faster payback period. So the idea is to pick the lowest hanging fruit that might be available in your plant and replicate that with a series of cobot cells that produce similar payback and ROIs. They do require integration from time to time, and we're going to talk about that in a little bit. The safety side of things. So the first thing that comes to mind when you talk about collaborative, the feature that it has to have a safety monitored stop. And that is used when a human enters the space of the robot, so the robot's range of motion. That triggers an auto stop response. And that is because there is a light curtain or a sensor set up to detect when there is presence of a human or another object in its way. Similar to number 1 is number 3, except that the cobot slows down based on the allowed forces and speeds spelled out in the safety standards from ISO and TS. This has been updated from 2011 and accounts for collaborative robots, not just industrial robots. The second one is a really cool feature, and that's path teaching. So basically allows the instructor pressing what essentially is the dead man switch on the teaching pendant and guiding the robot arm to those positions of the path that needs to be taken place for that particular operation. For example, in pick and place, you can teach the robot arm to grab part A, pick it up vertically, move it over in the x-axis, drop it back down in the z-axis, release the part. It's a very simple demonstration you might have even seen. And lastly, the power and force limiting. This is another unique feature to cobots. So there is a force torque sensor built into the end of the robot arm linkage that can feel the force and torque that's pressing up against it. For example, buffing, sanding, grinding applications where the end of the arm tool is one of those operations. It can replicate what a human would feel, the feedback from the part, and consistently apply that same amount of pressure when contacting the surface of the part that needs that surface treatment. It's a really neat feature. When demonstrating it, you can push and pull against it, and it will push back. Again, this is unique to a collaborative robot. Here's a quick demonstration video showing the safety side of these cobots.
The new concept of collaborative work between a person and a robot. And that's what this is going to demonstrate for you. You see, the robot is our 7-axis machine, and it's running at full speed in its zone. But as soon as I approach and enter into a collaborative area, the robot automatically slows down to 250 millimeters per second. This is the safety speed dictated by the new standard. It knows I'm in the zone because we have a safety-rated sensor, a laser scanner, that knows when I've crossed in. So I'm working in its area, and the robot automatically slows down. The robot's going to come in, pick up a component, and present it to me as the operator for an assembly process. So I'll go in, perform some assembly, and then have the robot reorient the part and reset it for the next pick position, and then bring it back to me. As it does that, now that I come back in, I'm allowed to work on this robot because it is at 0 speed. It is in a stop state. Stop state monitoring is one of the functions of the functional safety unit in this controller. So I'll step in, and then it's an iterative process. And now I violated it because I tried to go in while it was moving. That is a violation of stop state. So it makes sure that I'm clear of the zone, and then it will start again, and we'll go back to work.
So pretty cool video there showing just some quick functionality and safety features that the cobot has when linked up to a safety sensor. Looking at a side-by-side comparison between the cobot and the robot, you'll see some definite differentiators. Cobots are very much small and flexible. There are some higher payloads coming out on the market for sure, but for the most part, a lot of the applications are in environments where the speed is not necessarily as important as it is in a production, high-speed, high volume production environment where every half second matters, like it does in an industrial cell. The setup is fast. It can be days or weeks. If you're talking about an integrator getting involved, then you would add weeks onto it. But they are mobile. They are multifaceted. There is limited payload, and the speed of which it can move is also tied to that payload because the human factors that are involved when it comes to safely working alongside humans, lower upfront in cost as well. So compared to the industrial robots, as a rule of thumb, when you talk about adding the end of arm grippers, training, integration, all the other things that go along with the purchase of the robot itself, it's usually in the 25 to 50% range in addition to the cost of the robot. So whatever the robot cost is, if you took a 1.25 or 1.5 figure, that's generally going to be about the package cost for doing a full implementation of a cobot. Again, that's kind of the 80-20 rule. There's going to be instances on either side of that, but generally that's kind of a rule of thumb. So looking at now cobot versus human, what humans are good at: dexterity, creativity, reasoning, problem solving, ensuring safety. But we get tired. We lose interest. We lose focus. A cobot does not do that. So it's very complementary in that side of things. So it can be very repetitive. It doesn't mind doing monotonous, even dangerous tasks. And the human is going to be in charge of setting up a cobot safely so that collisions are avoided, that undue force and torque is not being put on the robot. It's moving at the right speeds depending on the payload that's it's working with, that being the part or the tool it's holding. So that's why cobots and humans are a good team. There was a study by Harvard which indicated that separated cobots and humans are much less productive compared to situations where they are put together as a team. In fact, the efficiency was 75% more compared to when each was left on its own. So where can we put cobots in a manufacturing facility, and what industries are using these? So you can see top left, some of the big ones are assembly, machine tending or loading and unloading, and again, those monotonous repetitive tasks. Some of the top reasons we see people invest in cobots are these three here: consistency in improving the quality and the quantity of your production, boosting that output, and then the big one, especially pre-COVID, but it's going to continue on even post-COVID, is that there's a shortage of skilled workers out there. Where those workers were in front of a machine all day and doing these repetitive tasks, those same workers can now be trained to operate a robot, to program it, to do the risk assessments, to do other tasks in the plant that are of higher value that a cobot can't do. In industry, these are the big ones: automotive and electrical, metalworking, but food and beverage and plastic and chemicals are also on the list. So it's a pretty diverse group when it comes to which industries are deploying industrial robots. Some examples of what that looks like on the floor: some pictures of a cobot on the left as a welding cobot. So you can see the welder there has been teaching the robot the path to lay the weld bead down, and it's still there at the cell monitoring the progress, doing the setup for the robot. While the robot is performing its task, the operator can walk away and set up the next job or maintain another cell simultaneously. So the efficiency gained here is that the operator, which was once just in charge of one cell, can now be deployed to multiple cells at the same time. On the right is more of an industrial robotic welding application where you've got a much larger articulating arm and a much larger workpiece. This video is going to show you what the simple steps are for setting up a cobot to do a machine tending application. Notice how the gripper is acting as both the door opener and closer, as well as handling the part. Sometimes a separate bar or link will be added to the end of the arm to perform that function, and some CNC machines have automatically controlled doors that open and close depending on the toolpath's completion. On the assembly side, we're going to look at some SCAR robots on the right. Again, these have a dual axis motion with an adjustment in the Z direction for extension and retraction. And on the left, this is a more advanced articulating pair of robots performing some furniture assembly. On the dispensing side, painting, certainly in automotive, with some large articulating robots. And then on the right, also an industrial articulating robot painting a front end of some sort of a vehicle, it looks like. Let's look at some pick and place applications. You can see here the part is being gripped, and then the tool, notice the tool profile has a piece added onto it that matches the profile of the gripper to make it much more easily handled by the robot. The human wouldn't have an issue grabbing that tool, but we had to add an additional part there to make the gripping function match the profile of the gripper. So there's an instance of using the gripper for both handling the part and a cutting tool, all in one cell. On a packaging side, we can have an end of arm tool or a gripper that is vacuum powered. So it can be a pneumatically driven external airline, or some of the grippers even have integrated airlines built into them now, or they just operate off of a electric solenoid. So there are different options depending on the gripping force and size of the gripper that you need. Another Cartesian robot showing you how a dispensing application could look with a nozzle on the end of the arm. And then on the right, you have another SCARA robot with a 4th axis dispensing arm. Again, applying some sort of adhesive or substance to the perimeter of this part. Let's look at a palletizing application. So here we have another vacuum gripper with an external airline, dropping a food package from one end of the line to another. So this is a demo version. It's just a short conveyor line, but presumably what's happening is there's some sort of a barcode scanner at the end of the line that's reading each code as it comes off. The robot is then pulling it off the line and then stacking it into a pre-programmed orientation, row by row, column by column, until the program is complete. On the application matrix side, let's look at where each type of robot fits. So if any of these are part of your plant, make note of the type of robot that might be a fit and compare and contrast the benefits of each. You can see articulating applies to most every application, whereas the Cartesian robot is probably the most limiting on the number of applications for manufacturing. So what does this mean? The challenge is not the robot, right? It's the other things. It's all the interfacing that goes around the robot. It's the programmer training that operator how to use it properly. How does the part feed into the robot in a successful manner, in a way that it's going to make a successful transition to the next cell? The tooling, the sensors that go along with the cobot, and of course safety. So we have to make sure the operator is safe, especially if the operator is going to be in close proximity to the cobot on a regular basis. So this is all referred to as the robotic cell from leanrobotics.org. Value stream mapping. Any of you who have been a part of lean manufacturing initiatives and training, Kaizen events, have probably seen a value stream map. Applying that to a robotic cell means you're eliminating the waste and optimizing the cell before you start to deploy the automation. We don't want to automate waste, right? We want to take the fat out and trim it down to a lean and mean process, and then apply the automation so that it sets up to succeed and give us the biggest ROI and the quickest payback period we can find. What that looks like on the right is where MEP centers can come in and help you do some of these value stream maps to eliminate those non-value added tasks prior to setting up the robot or automation piece. For iSmart, again, this is an MEP grant that's going to be in effect for the next 18 months plus. And these services that go along with the project are robotics assessments. So from here, if you're interested in having an assessment done, I'd encourage you to reach out to your local MEP center. We'll have our information here at the end for a no cost, no obligation assessment. From there, you'll be given an application evaluation. And I'm going to show you kind of what that looks like here. We'll help you develop the business case and line you up with the integrator, distributor, or trainer that is set up to perform best in your particular niche, whether that's assembly, whether it's welding. Some integrators are better at certain tasks than others. So we've identified those and we'll line you up accordingly so that some of that time and effort spent is already done for you. Your resources that you should be looking to outside of iSmart: local working groups for automation, networks of the big players in robots, such as ABB, FANUC, UR. They have quite a vast array of partners that have educational and training rooms, demo areas for you to see products in person. Grant funding, we can certainly help you with that, identify any grant opportunities that might be available in your locale. The training side of things, there's more to come with that. We've got some good momentum going with the Advanced Robotics for Manufacturing Institute, or ARM. They've done some boot camps in different parts of the country with great success in developing the workforce to program and run these robots. Several resources here for you to look at inside and outside of the iSmart program. What can our MEP do? Again, we can help you with the pre-deployment side, help plant leaders prepare workers for automation. It can be a shock culturally for first-time automation to be deployed in a plant. A lot of workers will see that as a threat. Robots are going to take our jobs. I'm going to be out of work as soon as this robot's online. What do I do? Well, the point of this program is not to eliminate workers. The point of this program is to upskill workers into higher paying, higher performing jobs, and for the robots to take on some of those tasks that are better suited for automation. We'll help you assist with the redesign of the process using Lean, like we just talked about, eliminating the waste, setting up the process efficiently prior to a full-blown automation implementation. And then post-deployment, what we want is to replicate those wins. Let's identify other areas that might be good applications for the same type of automation or different types. We focused on robots and cobots today, but there are certainly lots of types of automation, from indicator lights to safety light curtains to sensors, vision systems, lots of different types of automation out there that can be used by small and medium manufacturers with success. Here we have an example page of the implementation evaluation. So we will set this up as a date and time that works for the key stakeholders as well as our MEP team, and go through the pre-visit questionnaire with you, answer any questions you might have. This questionnaire will give us a little bit more information and background on your facility, your fully burdened rate, which we can use to plug in some of the calculations for payback period and ROI. And you can see on the right, the cell will have some documented photos, maybe even some videos, just showing more detail as far as what the operator is doing, the type of part that's involved in this cell. What are some of the automation drivers? What are the challenges that we see when we witness a typical operator on a day-to-day basis working in this cell? And then seeing what the throughput is, the cycles per hour. Are there multiple touch points? Is there downtime? Is the operator waiting for material or waiting on another cell? What are the opportunities here for automation? If you are looking into automation and have further questions, we are here to help. Please reach out to us depending on which state you're in, and we'd be glad to follow up with you to answer any questions, possibly set up a site evaluation. We're also doing virtual evaluations. So with COVID restrictions right now, depending on where you are, we will do some video or Zoom calls in lieu of being there in person and doing a plant walkthrough. So let us know if that's a better option for you right now. Thanks for your time today. Appreciate it. Send us any questions you have, and we'll see you next time.